In this video, we're going to continue our discussion of derivative applications and also learn one more derivative shortcut. At this point, we know quite a lot about finding the derivative. We have learned and hopefully memorized a few shortcuts. We know that for exponential functions, the derivative of e to the x is just e to the x. We've also seen that if there's a constant multiple, then our derivative, so derivative of k times e to the x is equal to k times the derivative, which is e to the x. And we've seen that for exponential functions with a base that is not equal to e, so derivative of b to the x, the derivative is equal to ln b times b to the power of x. We've also seen for trigonometric functions that the derivative of sine x is equal to cosine x, and the derivative of cosine x is equal to negative sine x as long as x is in radians. We have also explored a number of other derivative rules. So we have seen the constant function rule. So we know that if our function is just a constant value, its derivative is equal to 0. We know the power rule for when I have my variable raised to some exponent. I just bring that exponent down, it becomes the coefficient, and I subtract 1 from my exponent. The constant multiple rule, when my function is being multiplied by a constant. And we saw that we can explore this using product rule and end up with the same answer, where we find that if our function is some constant times another function, the derivative is equal to that constant times the derivative of that second function. We've seen the sum and difference rule, where the derivative of some function that is made up by adding or subtracting other functions, we can just find that each individual derivative and then add or subtract them together, just like the original function. And for the product rule, we've seen that, and this one's a little harder to describe, so we'll write this down, that if my function f of x is equal to g of x times h of x, then the derivative is going to be equal to g prime of x times h of x plus g of x times h prime x. Additionally, we've worked with the chain rule for composite functions where one function is inside the other, and we've seen that if f of x equals g of h of x, the derivative is going to be equal to g prime of h of x times h prime x. Or often we use the symbol u, so f prime x is equal to g prime u times the derivative of u. And sometimes we'll use our Leibniz notation and stuff. Not going to worry about that right now. You may have noticed, though, there's one kind of common function that we have not found the derivative for yet, and that is a rational function or a quotient function. And so you'll notice on our note here, it says the quotient rule for functions that are quotients, so rational functions, that this rule is optional. We may not need it. If you're not sure why, I'd like you to pause the video and think for a moment, what do I know about working with functions, or with ratios and with fractions? What do I know about dividing things? Is there another way of expressing it? I'm not going to answer that question yet, but keep that in mind. And let's think about, what do we do if we are told to differentiate a rational function? Consider the following rational functions, quotients. How could we rewrite them first and then find their respective derivatives? So just to be clear, just because sometimes we forget the vocabulary, sometimes we use it so often that we forget what it actually means. Quotient is what we get when we divide two things, and product is what we get when we multiply two things. So quotients means rational, and why do we use that word rational? Is it because they are logical or make sense? They're rational because they refer to a ratio, so this is a ratio, and so is this. So ratios and fractions are just different ways of expressing the same thing. So when we're talking about these fractions, we call them rational, referring to ratio. So you're probably aware of that already, but sometimes it's helpful to review the vocabulary and review our fundamentals as we work. Let's take a look at A. The first thing I'm going to do, sorry, there's a pretty loud siren outside. You might be able to hear that. My apologies. We're just going to power through though. First thing I'm going to do is get rid of my denominator. We're going to put it all on the same level. So I'm going to rewrite A as f of x equals 2 and 4x to the power of 3 plus 1 to the power of -1. Next up, we're going to find the derivative. So let's think about what tool we can use here. So it almost looks like product rule, and that I have, or a constant multiple rule. But we actually kind of have a function inside another function. We have something inside the brackets here that an operation is being performed on. So instead, I think it's better to think about it as a composite function. And so we're going to consider this as being our g of x, our g of u is our outer function, so that's going to be 2x to the power of -1. And so our derivative, g prime of u, is going to be -2x to the -2. Our u function is our h of x, that's inside, and that's going to be 4x cubed plus 1. And our u prime, so our derivative of h of x, is going to be 12x squared. Now let's go ahead and put our pieces together. And remember with chain rule that if our f of x is equal to g of h of x, then our derivative is going to be g prime h times h prime. And I'm being a little lazy with my notation here just because it's just a rough note off to the side. So let's go ahead and find our derivative. So f prime x is equal to g prime x, so -2x to the -2. And let's plug in our function u, which is our h of x, so 4x cubed plus 1. So the inside stays the same, and we're just kind of taking the derivative of the outside, so to speak. And then we're going to multiply by the derivative of the inside, so that's our u prime, or our h prime x, which is 12x squared. So what did we just use? We used our chain rule, and we used our constant multiple rule here. It all kind of blurs together. You just kind of start doing it naturally. You do your power rule, you bring down the exponent, you multiply by the coefficient, and you almost stop thinking about what tools you're actually using. Let's put this in simplified form now. Let's get rid of our negative exponents. Let's have positive exponents. So I'm going to have f prime x equals -2 times 12x squared. On the bottom, we're going to have 4x cubed plus 1 to the power of 2. And it's not negative anymore because I used up the negative, so to speak, bringing that term down to the denominator. And let's rewrite one more time. F prime x equals -24x squared over 4x cubed plus 1 squared. There's nothing else that we can simplify. There's no greatest common factor to take out or anything. So we're done. So let's label that as simplified. All right, I'm going to resize this a little bit so I have a little bit more room to work on B, and then we'll go ahead and answer B. One thing I will point out about A is that it is a quotient, so we are dividing one expression by another, but I was easily able to convert it into multiplying, and then it's just like a product rule question or a chain rule question. So kind of we don't need a separate quotient rule. We can just use the rules that we already have. Let's go ahead and take a look at B. So once again, I have a quotient, something divided by something else, and I'm going to start by rewriting it. So I'm going to express y is equal to x cubed minus 5x times x squared plus 1. And I'm bringing the 2 back up, so I need to bring the negative back, so to the power of -2. And what rule can I use here? Well, I can think of this as two expressions being multiplied by each other. So we're going to go ahead and use our product rule. And also we're going to use chain rule. So our parts here, this expression and this expression are multiplied together. So think like A times B, and that's where we're going to use product rule. But when we want to find the derivative of this component, we see we have one function inside another. So my g of h of x, it's going to have g is x squared and h is x squared plus 1. Sorry, x to the -2. So we're going to need to combine product rule and chain rule here. So this is going to take a couple steps. Once again, I always find it helpful to write out the rules I'm going to use. So if you have some kind of formula sheet in front of you, you can use that. Or I'm just going to write it off to the side here. I'm going to remind myself that product rule is when I have f of x equals g of x times h of x. That f prime x is equal to g prime x times h of x plus g of x times h prime x. And then for chain rule, I know that if f of x is equal to g of h of x, then I'm going to have my derivative equal to g prime h of x times h of x. And I always find it helpful to kind of write off to the side like I did here what my g and my u are and everything. So I'm going to do that right away. So I'm just going to focus on this chunk here because it's the composite portion of my overall function here. And so let's go ahead and label our pieces. So I'm going to have g of u. So what is my function? It's going to be u to the power of -2. I'm going to find the derivative. G prime u is -2, u to the -3. U is my inner function, so x squared plus 1. I'm just going to add an extra label here. Remind ourselves that u is equal to my h of x as well. So u equals h of x equals x squared plus 1. And when we find our derivative, h prime x, we're going to have 2x. So now we have all the pieces we need to put together our product in our chain rule and differentiate this function. So we're going to differentiate the second function using chain rule. Let's go ahead and do that. So I'm going to have g prime, which is -2, u to the -3, and u is x squared plus 1, times u prime, which is h prime of x, which is 2x. And then we have our original term here, x minus 5x. Actually, I guess we can't even say that yet. I can't write that yet because we need to differentiate using product rule as well. So all we've done so far, I'm going to move this over, is find the derivative of what's in the blue box. So I'm going to move that over, and then we'll come back. All right, so that's the derivative of that second function. Let's leave that off to the side for a moment. And now let's apply our product rule. So product rule tells us that our dy dx is going to be equal to g prime. So the derivative of our first factor here, which is this part right here. So we're going to have 3x squared minus 5 times h of x, which is our second factor, so x squared plus 1 to the power of -2, plus, and we're going to have our g prime, or sorry, g of x, so x cubed minus 5x, and then we're going to have our component right here, which is our derivative of our second function, our h of x. So I'm just going to, once again, just move that down into position. And now that that's in place, we'll indicate that we are multiplying, and I'll just do it like that. So it's a little bit messy, but that's fine. We can work with this and fix it up. So let's rewrite this a little more neatly. We're going to have 3x squared minus 5 times x squared plus 1 to the power of -2 plus 4x times x cubed minus 5x times x squared plus 1 to the power of -3. Whoops, not quite. We missed one thing. When I took this derivative, then this is negative. So 2x times -2 is going to give us -4. All right, that looks a bit better. Now we want to simplify, and so we're going to look for any common factors. And the common factor that I have is going to be x squared plus 1 to the power of -2 and to the power of -3. And so we can factor out the x squared plus 1 to the -3. Because remember, to the power of -3, it's actually going to be smaller than the -2. So let's do greatest common factoring. And I'm going to have x squared plus 1, and we can factor out the negative 3, and we're going to be left with 3x squared minus 5, and x squared plus 1 to the power of 1, which I don't need, but I'll write it just so we can keep track of our exponents, minus 4x times x cubed minus 5x. Finally, we're going to expand. We're going to collect our like terms, and we're going to write our exponents in a positive manner. So I'm going to have on the bottom x squared plus 1 to the power of 3. On the top, I'm going to use my distributive property and multiply these out. So I'm going to have 3x to the power of 4 plus 3x squared minus 5x squared minus 5. And we do the same thing over here. Distribute. So we are going to have minus 4x cubed plus 20x squared. Let's identify our like terms. So I have my x to the power of 4s. So I'm going to have 3 minus 4 is negative x to the power of 4. Next up, I have my squared, so 3x squared minus 5x squared plus 20x squared. 3 minus 5 is negative 2. Negative 2 plus 20 is positive 18. X squared, and I'm just left with my negative 5, so minus 5 over x squared plus 1 to the power of 3. So this is our dy dx. This is obviously a little bit shorter than what we had up top, and this is our simplified form. And that's all we had to do. Once again, it took a few steps, but nothing is particularly new. It's just a matter of keeping track of everything that makes it challenging. And we're not going to worry about this right now. I can't actually edit the background of these notes, so we just have to work in the space provided.